Hello everyone and welcome to Module 11. We'll talk about nonparametric analyses. First we'll talk about the logic of these kinds of analyses, and then we'll talk about two different kinds of nonparametric statistics, logistic regression and chi-squares. Nonparametric tests are different from parametric tests in that they don't make assumptions about the shape of the population distribution, and so they don't make these assumptions about normal distributions. And nonparametric tests don't necessarily involve the estimation of population parameters. Most of them don't, which is why they don't have that assumption about what the population looks like or what those distributions look like. Most of these analyses or most of these tests can be applied to categorical outcomes or to continuous outcomes that aren't normally distributed. So when we violate those assumptions of normality, there are many nonparametric tests that can help us still answer the questions that we have, even if the distributions don't meet the assumptions of many of the parametric tests. So these give us a whole other range of options when we might violate assumptions or have variables that are categorical, outcomes that are categorical. So we'll talk first about logistic regression, extending what we know about linear regression to examine regressions that can be applied to categorical outcome variables. And so this would be a situation in which you would have an outcome variable that is often the absence or presence of a specific characteristic or behavior, for example, or a diagnosis. In binary logistic regression, we have a two-category outcome variable, a dichotomous outcome variable. In multinomial logistic regression, we have categorical outcome variables with more than two categories or more than two levels. And our independent or predictor variables can be either continuous or categorical. Logistic regression is ideally suited for some mixture of categorical or continuous predictor variables. And logistic regression revolves around the idea of odds ratios. And so in logistic regression, we're trying to predict the odds of being in a particular category. And so we're using often a set of independent variables or predictor variables to determine the odds of being in either category. And so our odds ratios, anything that's equal to 1 or roughly equal to 1 indicates that you have an equal probability of being in either category. Greater than 1 indicates that the probability of being in a category with the unit increase in independent variable is higher than at the original value of the independent variable. And less than 1 means that the probability of being in a category with unit increases in the independent variable is lower than at the original value of the independent variable. And most of you are probably thinking that doesn't make a whole lot of sense and you're trying to wrap your head around that, and that's okay. I think it'll become much more clear once we go through an example and I talk a little bit more about what these odds ratios mean and what they look like. So some kinds of research questions that we can answer using logistic regression are similar to what we asked when we talked about linear regression. In linear regression, I asked, does substance use predict the frequency of sexual risk behavior? And in this situation, I'm asking, does substance use predict engagement in sexual risk behavior? So yes or no, does somebody engage in sexual risk behavior? And does their frequency of substance use predict whether they engage in sexual risk behavior? Similarly, does sensation seeking predict whether or not somebody engages in sexual risk behavior? And the example that we'll go through in this module lecture is still sticks with the contraceptive self-efficacy variable that we've been using all semester from the AdHealth dataset. But we're looking at this now as an independent variable and looking to see if contraceptive self-efficacy predicts contraceptive use. And that is a yes or no dichotomous outcome. Logistic regression has a few assumptions, though not as many as parametric tests because it doesn't have all of the distribution assumptions. You, again, have to have a categorical dependent variable. This is what this is designed for. You still want minimal multicollinearity of your independent variables. And so when you have multiple independent variables in your model, you essentially want to make sure that those variables aren't capturing the same thing, that we're not using multiple variables that are essentially completely overlapping with one another. So we want to make sure that these are somewhat separate. And even if we have a significant relationship, so for example, a significant correlation between two continuous predictor variables, as long as that correlation is not too big, we're still okay. We essentially want to know that those variables don't overlap completely. So we want to look at what those correlations are and think about whether or not those are big enough to count as multicollinearity. And then we want to know that we have independent observations. So for example, on our outcome variable, whether that's contraception use or sexual risk behavior or something like that, we want to know that people can't be in both categories, that those categories are independent of one another. So let's run through this 4-step process and then run through an example in SPSS of logistic regression. I didn't assign the reading in the Huck textbook, but if you want to go ahead and read that section in the Huck textbook, you can get a much more thorough introduction to logistic regression. In many ways, the idea of regression is very similar, whether it's a multiple linear regression or a logistic regression. This is a special case of regression in which we have a dichotomous outcome variable. So using this 4-step process, we'll state the null and alternative. In many cases in this situation, we're interested in the odds ratio for specific predictor variables. We can also talk about the full model and how well it does in predicting group membership or classification into one or the other of the categories in a binary logistic regression. So when I give you an example, I'll talk about the null and alternative hypotheses from the full model as well. But we're often talking about this odds ratio here. And so in this situation, we're not talking about something being different from 1. We're not looking at mean differences anymore. We're looking at differences in the odds ratio here. And as I mentioned before, an odds ratio of 1 indicates that you have equal probability of being in either category. And so our null hypothesis in this situation is that odds ratio is 1. That there's a chance that you're going to be in one or the other category. And so we're saying that the null hypothesis, that odds ratio is 1. In the alternative hypothesis in this situation, this is non-directional. We're saying that the odds ratio is not equal to 1. So it's either bigger than or less than 1. We want to ensure that we meet the test's assumptions. We have a categorical dependent variable, minimal multicollinearity of our independent variables, and independent groups. We want to calculate the test statistic and make a decision and interpret our results. So very similar steps that we go through. We'll always use SPSS in this situation to calculate this test statistic. And then when we make this decision, we'll look at the p-value, we'll look at the size of the odds ratio and the direction of that odds ratio. We'll also look at the predictive power and the classification accuracy of the full model. And then we'll talk about clinical and practical significance, as we always do. So let's run through a full example in SPSS. I'll run through it here and then I'll switch over to SPSS and show you how I did that. So we're going to come back to this question. I said in that original question, does contraceptive self-efficacy predict contraceptive use? I'm going to show you a slightly more complicated example in which we have 2 predictor variables, gender and contraceptive self-efficacy. So we have a categorical variable and a continuous variable, both predicting a dichotomous outcome variable. So for our null hypotheses, we can talk about a model hypothesis. The model is evaluated in logistic regression via a chi-square. And we'll talk about the chi-square in the next section of this module, but this is what this statistic looks like. And so we're going to say that our full model chi-square does not accurately predict contraceptive use or account for variation in group membership. We can say this a few different ways. And we can talk about our null hypotheses for each of our odds ratios as well. So if we're talking about the gender odds ratio, we would say contraceptive self-efficacy does not predict contraceptive use. Sorry, that should be CSE under the odds ratio here. So we would say contraceptive self-efficacy does not predict contraceptive use. Alternative hypotheses, this full model one is this same thing but does not equal 0. The full model does accurately predict contraceptive use or accounts for significant variation in group membership. For this one, we might look at the odds ratio for gender and say gender does predict contraceptive use. So this odds ratio is less than or greater than 1, but it's not equal to 1. We could do a directional hypothesis. Some of you were asking about that in a Google Hangout recently. And so we could say we think that the odds ratio will be greater than 1 or less than 1. And so we could do that for both the contraceptive self-efficacy and the gender variable. So we could look at that in a couple of different ways. Doesn't change what we do in our tests if we make it a directional or non-directional hypothesis. So we'll also check that our assumptions are met. So we have the 3 variables in here. We have a categorical dependent variable. Contraceptive use is yes or no. So that is in fact a dichotomous categorical dependent variable. We have minimal multilinearity of our independent variables. So we looked before at gender and contraceptive self-efficacy. There is a significant difference there. That effect is not huge. And those variables don't overlap entirely. So we're not so worried about them having some relationship with one another as long as they are not 100% related. And then we also know that our observations, our categories, are independent of one another. So people can't be both yes and no in contraceptive use. So then we'll conduct the test. This is what this looks like. We'll come to the results. I'm actually going to switch over to SPSS now and run through this example. So I moved some of these variables up to the top so that we could see them here. So if we look at most recent birth sex or birth control use at most recent sex, we see that we have, in fact, no and yes here. In this situation, we also have you only had intercourse once, and so that's counted as a missing variable in this situation, but they didn't have it coded as missing. And so I went over here to the missing, and before there was only 7 here, and I actually added 3 in here so that we have a dichotomous variable. Without that in there, SPSS doesn't like to look at this variable in a binary logistic regression because it thinks that it has 3 levels of the category. So I did change that a little bit. We have our contraceptive self-efficacy scores here, and we have biological sex here. In this situation, we do have to note how these are coded. So in this situation, male is 1 and 2 is female. Most people like to code their variables as 0, 1 for a variety of reasons in terms of that are related to interpretation of the intercepts or the constants in your models. But we'll leave this as is for right now, and I'll talk a little bit about how we interpret the odds ratio based on what these numbers are. So we have these 3 variables that we need in here. For those of you who are using birth control at most recent sex as your as a variable in any of your models, some of you are using it as an outcome variable. For these purposes, we're not going to recode this variable right now, but we might, depending on what your question is, we might want to recode this variable. So for example here, if they said that yes, they used birth control during their most recent sex, they got 3 follow-up questions about the kinds of methods of birth control that they used. So they could report using up to 3 different methods. So for some of these people, you see that they used condoms and birth control pills. That was true for several people, or condoms and withdrawal. And so if we keep kind of scrolling down here, we can see that for some of these people, some of them used effective methods for, in both situations, so both birth control and condoms, NuvaRing and condoms. For many of these people, though, right in here, they used withdrawal as their first method that they reported. So some of them, it's just the ordering of things. They use withdrawal and they use birth control pills. So that's still an effective method of birth control. For others, they wrote in withdrawal and then nothing else. So they said that they used birth control because they were pulling out. We can talk about whether or not we want to count that as birth control. So they reported that they did use birth control, but in fact what we see is that they used withdrawal. So depending on what your question is and how you might want to think about birth control, we may want to think about changing the people who said that they used withdrawal and nothing else as no on this variable. So I think I have meetings set up with many of you who are using this this outcome variable of whether or not they use birth control. So think a little bit as you work on your analysis plan and your data cleaning information as to how you might want to treat people who said yes and only reported using withdrawal. So that's an aside. Let's go ahead and do this logistic regression. And so we're looking at contraceptive self-efficacy and gender as a predictor of yes or no people have used birth control. So we're going to come up here to analyze, to regression, and we're going to go to binary logistic. So we'll come over here, and then most recent sex birth control goes in the dependent variable. And then we'll look at biological sex and contraceptive self-efficacy. It's really only one small thing that we need to do here. We need to tell SPSS which of these variables are categorical versus those that are continuous. So we'll put biological sex over here. We'll leave the indicator as it is. Right now the reference category is the last category or the highest category. So in this situation it's using females because they're coded as 2 and males are as 1. So it's comparing males to females in this situation. And so we don't have to change anything else. We can always add in different tests. A lot of people like the Hosmer-Lemmischau goodness of fit test. Some people like to have the confidence intervals in there. But for right now, we're just going to leave that as is. And so we don't have to change anything else or do anything else. Much like in linear regression, you can enter your variables in a variety of different ways. So forwards, backwards. You can do different steps, but we're just going to put both of these variables in simultaneously, and all we did was tell SPSS which of our independent variables is categorical. So we'll hit OK or paste to create the syntax, and then this is creating our outcome up here for us, our output. And so this gives us a little bit more output than the regular linear regression does. So let's work through a little bit of this. Really, we're not going to start interpreting anything until we get to block 1. This block 0 is our outcome without any predictors in the model. And so it's not including biological sex. These are not in the equation. It's not including contraceptive self-efficacy. And so we're just going to mostly ignore all of that and start here at our first block. So this first thing that we're looking at is our overall test of the model. And as I mentioned, this uses a chi-square. Because we entered everything in one step, all 3 of these are the same. Step, block, and model are the same. So our chi-square value is 81.96. Our degrees of freedom is 2. And our significance is p is less than 0.001. Another model statistic that we'll look at, these are R-squared values, and these are typically interpreted fairly similar to how the R-squared values in regression are interpreted, and as they are in correlation as well. And so in this case, a lot of people prefer the Nagle-Kirkes R-squared. So in this situation, we would say 7.9% of the variability in contraceptive use can be explained by both of these variables being in the model, gender and contraceptive self-efficacy. So again, this is a fairly small effect that we're looking at here. And in this classification table, what this tells us is, knowing the information that we do about gender and biological sex, how accurately are we able to predict which category people are in, whether or not they've used birth control. And we accurately predict 73% of the time. So that's actually pretty good. Although if we look up here at this beginning block, this with nothing in the model, how well would we predict contraceptive use? And that's 72% roughly. So just by chance, we would predict 72% correctly. And then with both of the variables in the model, we predict 73% correctly. So again, this very small effect. We're not getting all that much better with the variables that we have in the model. But when we come down here to variables in the equation, this is where we can start to interpret these individual variables as being predictors of contraceptive use. And so in this situation, we have biological sex here. And so we're comparing males to females in this situation. And so we have our unstandardized b-value here. This is the statistic that it uses to determine the significance of each of these predictors. It's a Wald's test, which is somewhat similar to a t-test. But really what we're looking at here, obviously our significance value first to make sure that we actually have a significant predictor. But we're interpreting the exponentiated beta here. And so this is our odds ratio. And so I'll show you a couple things. First, let's talk about the biological sex variable. So this is comparing males to females. And so what this is telling us is that males are 1.59 times more likely to use contraception than females. What we're seeing here is a exponentiated beta that is greater than 1. You'll see over here this value is a positive value, and this value is greater than 1. This value for contraceptive self-efficacy is a negative value, and this exponentiated beta is less than 1. So you'll see that correspondence there between what those values are. The biological sex variable tells us that males are more likely than females to use contraception. And we can also see this if we run just a simple chi-square and look at the percentages of males that use contraception and the percentages of female that use contraception at their last sex. It'll be interesting to see how that might shake out differently if we get rid of those people who only used withdrawal. And then when we look at this contraceptive self-efficacy variable and interpret that, we go over here, we see that it is a significant predictor. And then we come over here and we have 0.806. So we need to think about how to interpret that a little bit. And so this is a negative relationship here. And so let's go back to our analyses, and I talk about each of these a little bit more. So again, we're coming in here and we're interpreting this exponentiated beta. And so we want to think about how to report that. And so I'll do the big picture and then I'll talk about contraceptive self-efficacy specifically, because I think it's a little challenging to interpret some of the continuous predictor variables. So in this situation, we would say we conducted a binary logistic regression wherein contraceptive self-efficacy and gender were entered as predictors of contraceptive use. Typically, you want to tell your reader how your categorical independent variable was coded. The full model was significant. This is all the full model statistics, correctly classifying 73.1% of cases and accounting for 7.9% of the variance in contraceptive use. You probably would want to indicate which pseudo R-squared, as they're called in logistic regression, that you're using, the Nagle-Kirkes versus the Cox and Snell. Contraceptive self-efficacy significantly predicted contraceptive use, and this is our beta value, or exponentiated beta value here. And we interpret that as for every 1 point decrease in contraceptive self-efficacy scores, again, remember that's a negative value on the beta and less than 1 on our exponentiated beta. So for every 1 point decrease in contraceptive self-efficacy scores, the likelihood of contraceptive use at the last sexual encounter increases 19.4%. And so we have to think about the multiple, sort of the double negatives that we have in this situation. So decreases in contraceptive self-efficacy are actually increases in the construct of contraceptive self-efficacy. So remember, higher scores indicate lower levels of contraceptive self-efficacy and vice versa. So what we actually see is that for every 1 point increase, essentially, in the construct of self-efficacy, the likelihood of contraceptive use at the last sexual encounter increases 19.4%. And we get 19.4% by turning this 0.806 into a percentage. And we can do that by subtracting it from 1. The technical formula for that is 0.806 times 100, and then that value minus 100. And so that will allow us to translate that into percent. We can say this in a variety of different ways. But this is one of the ways I think that's helpful to think through the interpretation of these coefficients. And then, as we talked about before, gender significantly predicted contraceptive use, indicating that males were 1.5 times more likely than females to report contraceptive use at their last sexual encounter. And we can change this into a percentage if we want to. So if we do 1.59 times 100, minus 100, then that gives us 59, so 59% more likely than females to report contraceptive use at their last sexual encounter. We can also just subtract that from 1 and get the value of that. So this is how we interpret the full model and each of those individual coefficients. I'm not going to spend a ton more time on logistic regression. We would think about both the clinical and practical significance of this in much the same way as we have been before. Thinking about why it might be that gender predicts contraceptive use in this way, It makes sense that contraceptive self-efficacy predicts contraceptive use in the way that it does. And one final thing to note with each of these is that each of these predictors is evaluated in the context of the other predictors. So much like we talked before in multiple regression, each of those predictors is evaluated at the average level of the other variables in the model. So these would be slightly different if we ran a logistic regression with just gender as a predictor or with just contraceptive self-efficacy as a predictor. This would change a little bit. So let's talk about chi-squares next, and I think you will find chi-squares much easier. This will be, I think, in some ways conceptually easy to understand. And this might help you understand logistic regression a little bit in understanding chi-squares as well. So chi-squares calculate the difference between the observed frequency of a category in a categorical variable and a theoretically expected frequency. The observed frequency is the actual number of times each category occurs in a variable, so the number of people in a category typically. The expected frequency is a theoretically predicted frequency based on the null hypothesis. We can talk a little bit about how we might create that. If we have one sample chi-squares or one-way frequency tables or goodness of fit tests, then we can create that null hypothesis based on just a distribution of scores. So if we have three levels of our categorical variable, we might expect for a third of our people to be in each of those categories. So that might be what we use as our null hypothesis. We may have some other theoretical idea of how people should be distributed across those categories and want to compare to that, those values and those proportions. If we have more than one variable that we're looking at, more than one categorical variable, we would conduct a chi-square test for independence. We'll create a contingency table, and we want to know if the proportions that we're looking at are independent of one another, if the variables are independent of one another. So the degrees of freedom are based on the number of columns, -1, multiplied by the number of rows, -1. I'll talk about this in just a second, and I'll show you how to assess this, but one of the assumptions of chi-squares is that all the expected frequencies should be at least 5. So if more than 20% of your cells have an expected frequency of less than 5, the chi-square is not appropriate. We could use a Fisher's exact test. I'll talk about that in a bit. So some research question examples that could be used for chi-squares. Are white men more likely than men of color to meet diagnostic criteria for sexual compulsivity? So we looked before in an ANOVA at race and ethnicity as predicting sexual compulsivity scores, but then we could split people up based on their diagnostic criteria for sexual compulsivity. So we talked about that score of 24 or more being sometimes used as a cutoff. Are gay and bisexual men who meet diagnostic criteria for sexual compulsivity more likely to meet alcohol abuse criteria than those who do not meet sexual compulsivity diagnostic criteria? So this would be a situation in which we have 4 cells of people, those who do and do not meet criteria for sexual compulsivity, and those who do and do not meet criteria for alcohol abuse symptoms based on the audit. As we talked about with the audit before, a score of 8 or above is often considered as indicative of alcohol abuse. So we could split people up according to that continuous score and then end up with a categorical variable, and we could compare and see if sexual compulsivity diagnosis is independent of alcohol abuse diagnosis. In the AdHealth data, we might ask, are girls or boys more likely to take a purity pledge? So this is in some ways a descriptive question, although we can test to see if these variables are actually independent of one another. So is gender independent of taking a purity pledge? And so following that particular question, this is what this contingency table would look like. We essentially have this 4-cell situation here. So we have males and females. We have those who took the purity pledge and those who did not take the purity pledge. And we have just these raw numbers in here. So there are 195 men in the AdHealth data set, or boys in the AdHealth data set, who took the purity pledge. There are 369 girls who took the purity pledge. There are 2,031 boys who did not, and 2,053 girls who did not. So we get the total number who took the purity pledge the total number who did not take the purity pledge. This is the total number in the full sample. And we also get the total number of males, the total number of females. So we can actually look via chi-square and find out if these percentages are different from one another. So it's not looking at the raw numbers here, it's looking at the proportion. And so I'll talk about how to interpret those different proportions and what proportions we're looking at specifically. The assumption of the chi-square is that we have categorical variables. Much like a correlation, we don't necessarily have to think of these variables as being independent or dependent variables. In this particular situation, gender can't depend on anything else. It has to be an independent variable. And so we are considering gender as an independent variable in this situation. As I said earlier, the expected cell frequencies have to be at least 5 for each cell, or we'll use the Fisher's exact test, and I'll show you how to look at that. And again, our observations or our categories have to be independent of one another. So individuals can only be in one category on each variable. Those categories can't overlap. So using this 4-step process, we would state the null and alternative. The null hypothesis is that the two variables are independent of one another, that they don't have anything to do with one another. And the alternative hypothesis would be that the two variables are not independent of one another, that they do share, they have some overlap. And so we want to make sure we meet the test assumptions, that we have categorical variables, expected cell frequencies of at least 5 for each cell, and that our categories are independent. We calculate the test statistic, and we make a decision and interpret our results. We'll do that in SPSS. This formula is actually not all that terribly complicated, and I think your book runs through this formula. The formula essentially compares the observed values to the expected values to look and see if those are significantly different from one another. In this situation, we're looking always again first at our p-value, and then we want to look at the variations in our expected versus observed frequencies. And we want to look at these proportions and see what proportions are bigger than one another. And then always think about our clinical and practical significance. So let's run through an example of this in SPSS. We're going to follow this research question of, are males or females more likely to take a purity pledge? Our null hypothesis are that gender and purity pledge are independent of one another. An alternative hypothesis are that gender and purity pledging are not independent of one another, that there is some overlap there. We do have categorical variables. Gender is yes, no. Purity pledging is yes, no. We do, all of our expected cell frequencies are at least 5, but I'll show you how to check this in the chi-square test. And we do have independence of observation. So people can't be categorized as both male or female and as having taken or not taken a purity pledge. So we'll conduct this test, and I'll switch over to SPSS again now and show you what this looks like. And then we'll come back and interpret the results. So let's go back over to SPSS. Again, I've moved all of these variables up to the top here. So we have biological sex. Again, this is male or female. In this situation, we have 0 or 1 for yes or no. So in this situation, we can look and see, we can use this chi-square to see if these variables are independent from one another. So chi-squares are under descriptive statistics, actually. You can get to them in a couple of different ways, but we're going to go under descriptive statistics and go down to crosstabs. So under crosstabs here, it doesn't necessarily matter which we consider our row and which we consider our column. So in this situation, we'll put gender or biological sex in our row, and we'll put taken purity pledge into our column. And we have to tell it to give us a chi-square. So there's a bunch of different statistics we can run via crosstabs. Some of these we've talked about a little bit before. We talked about Kendall's tau B and tau C a little bit. We haven't talked about many of the rest of these, but for right now, we're just going to do chi-square. So we'll hit continue. And then I actually like in cells, I actually want, right now what it gives us is just the observed, so just the number that we see. I also like to see the expected, and I like to see the percentages because you're going to want to calculate those anyway, and so I actually like to do row, column, and total. And I'll show you how to interpret those in a couple of different ways. You might want to do them just according to one of the variables. It can be a little confusing to interpret these, so I'll show you how to do it, and then you can choose to do that in slightly different ways. So let's hit OK. All right, so what we see here now is that we have this contingency table. So this is the same thing that we looked at before in the table that I presented in the PowerPoint. So we have, of males, we have 195 took a virginity pledge. For females, 369 took a virginity pledge. For males, 2,031 did not, and 2,053 of females did not. So those are just our raw count numbers of the people who are in each of these categories. And then we have our expected count. So sort of based on what this distribution looks like, this is what we would expect in each of these, that 270 of those of boys would be in this category, and 293 of girls would be in this category. And this is based on just what this variable looks like in this data set and the percentage of people in total who fall out into these categories. And so essentially what this test is doing is comparing the 195 to 270 and the 369 to 293. And it's doing that to look and see whether those differences between expected and observed are different for males and for females. And so let's just go back down to this chi-square test, and then we'll come back up and talk about these percentages. So our Pearson chi-square, which is the one that we are looking at in this situation, our value is 45.62. Degrees of freedom is 1, so this is the number of rows, 1, 2, minus 1, so we have 1, times the number of columns minus 1, so we have 1, 2, minus 1, which is 1, so 1 times 1 is 1. And then our p-value is less than 0.001. So this is typically the chi-square value that you're going to look at, this top one right here. You'll see right after this value a little a here. And if you come down here, it says 0 cells have expected counts of less than 5. So we know that we've met that assumption because the test is actually telling us so. Let's go back over here, and I'll show you the rest of these within within PowerPoint. So what we're looking at here, so we have each of these same values that I already went over, the counts and the expected counts. And now let's look at these frequencies. So this is when I was asking it to give me the percentages according to the rows and the columns. These are the two different percentages that it's giving us. And so we want to interpret this top one within biological sex, and I'll talk about interpreting both of them. But within biological sex, we have of the men, so of all of the men, 8.8% of them took a purity pledge. And now we come down here and say the percent within biological sex. Of the women, 15.2% took a purity pledge. And so those percentages are fairly different from one another. And so what this chi-square of independence is doing is telling us if these two variables are independent of one another. And these are the percentages that we're interpreting. It's the question that we want to know is, are males or females more likely to take a purity pledge or virginity pledge? If we have this other percentage down here, so this is the percentage within this taking a pledge to maintain one's virginity. So within those who took a pledge, we can say that 34.6% of those are male and 65.4% of those are female. So these two add up to 100% because we're looking at 100% of those who took a purity pledge. And we see that most of those are girls and not boys. So a higher percentage of those are girls and not boys. And then we would say of men, or of males, 8% took a purity pledge, whereas of females, 15% take a purity pledge. So we could interpret that in a couple of different ways. I think it makes the most sense, based on our question, to look at within biological sex. And so we know, again, that this is a significant chi-square, and we would interpret that as such. This is what this chi-square looks like, 45.62, p is less than 0.001. We know we met this assumption of having a minimum expected count of at least 5 in all of those cells. And so we could say a chi-square of independence indicated that females were more likely than males to take a purity pledge, with 8.8% of boys taking a purity pledge and 15.2% of girls taking a purity pledge. And so then we could talk about, is that effect very big? There is an effect size that you can calculate for chi-squares. That's called a Cramer's phi. I can give you guys the information for that if you're interested in it. But looking at these percentages also gives you a pretty good sense of how big that difference is. So for the assignment for this module, as always, you'll download the data set and answer the research question proposed in the assignment. And this is the question that we talked about earlier. So compared to those who do not meet diagnostic criteria for sexual compulsivity, are those who meet SC diagnostic criteria more or less likely to also meet alcohol abuse diagnostic criteria? So are the variables of sexual compulsivity diagnosis and alcohol abuse diagnosis independent of one another? You'll write up your results section. There's no tables or graphs required in this one. And if you have any questions about that or about chi-squares or logistic regressions in general, certainly send me an email, post under the forum, and let me know. Thanks.